All right, today we're going to do something that feels a little bit like magic. We're going to uncover a really famous theorem from number theory, not with a bunch of crazy equations, but by playing a simple game, with beads on a string. Let's dive in.
Okay, so here are the rules to our game. It's pretty simple. First, you pick a number of beads for your necklace. Second, you get to color each bead from a set of colors. We'll start with red, green, and blue. Third, and this is the big one, we're going to say two necklaces are the same if you can just rotate one to look like the other. And last rule, no flipping the necklace over. That's it. Simple, right?
So here's the core idea, the secret sauce, really. When you take a necklace that has a mix of colors and you start rotating it, you create this whole family of colorings that we count as just one single necklace. And here's a little spoiler for what's coming. Prime numbers are going to be the heroes of this story. They make these families incredibly neat, creating these perfect little packets that make counting them way easier than you'd think. Okay, let's get our hands dirty and actually try this out. We're going to start with a prime number of beads, 5 of them, and our 3 trusty colors, red, green, and blue. This is our first test run to see how this whole rotation thing really plays out.
You know, whenever you're trying to count something kind of tricky, the best strategy is always to start with the easy stuff first. So for us, that means finding the necklaces that are just one solid color.
And here they are. You can have an all-red one, an all-green one, or an all-blue one. The thing that's so special about these is that you can spin them all day long, and they look exactly the same. They're kind of super symmetric, you could say. So that's exactly 3 of these special, unchanging necklaces. Let's just put those aside for a second.
All right, so we've got those 3 simple, solid color cases out of the way. But what about literally everything else? You know, all the other possible ways you could mix and match those reds, greens, and blues. How in the world do we count those?
And this, right here, is where the magic of using a prime number really kicks in. Because we chose 5 beads, a prime. Any necklace that isn't a solid color will give you 5 totally distinct, different-looking patterns as you rotate it. This means all the other possible colorings get bundled up perfectly into what we can call 5-packs. So how many arrangements are actually in these packs? Well, first let's figure out the total ways we could color the beads if we just ignored rotation for a second. You've got 3 color choices for each of the 5 beads, so that's 3 times 3 times 3, or 3 to the power of 5. Now from that grand total, we just subtract the 3 solid color necklaces we already counted. This number right here represents every single coloring that belongs in one of those 5 packs.
So here's the punchline. Since every single one of those remaining colorings gets bundled up neatly into a 5-pack, the total number of them has to be perfectly divisible by 5. There can't be any leftovers, right? It's not a guess, it's just structurally how it has to be.
Okay, I know what you might be thinking. That's a neat trick with the number 5, but is that just a fluke, a coincidence? And you know what? That is exactly the right question to be asking. The only way to know if we've really found a pattern is to try it again.
So let's try another prime number. How about 7? If we have 7 beads and 3 colors, guess what? The exact same logic holds. You've got your 3 solid color necklaces. And everything else? Every single other combination of colors falls into a perfect 7-pack when you rotate it, which means that 3 to the power of 7 minus those 3 special ones just has to be divisible by 7. Wow, the pattern holds.
So by now you've definitely noticed a theme, right? We keep using prime numbers, like 5 and 7. And you're probably wondering, hey, what's so special about primes? Does this whole beautiful system just fall apart if we don't use one?
And the answer is a huge, resounding yes. This whole thing works so cleanly because the number of beads is prime. If you tried this with a non-prime number, like 6, you could make a pattern like red, blue, red, blue, red, blue. And that repeats after only 2 rotations, not 6. It breaks our perfect packets and makes the counting a whole lot messier. Primes are what keep it simple.
And that lets us see the general rule. For any prime number of beads, we'll just call it P, the pattern is exactly the same. The total number of ways to color them with 3 colors is 3 to the power of P. And that's equal to our 3 special solid necklaces plus a whole bunch of P packs. It means that 3 to the power of P minus 3 will always be divisible by P.
Now mathematicians have this really slick, elegant way to write this down. This whole idea of divisibility is captured by something called modular arithmetic. When we say that 3 to the p minus 3 is divisible by p, it's the exact same thing as saying 3 to the power of p is congruent to 3 modulo p. It's just the formal way of saying the exact pattern we found with our bead.
Okay, this is getting really cool. We found this deep pattern that works for any prime number of beads as long as we use 3 colors. But what about the colors? Is 3 some kind of magic number too? What would happen if we used 4 colors, or 10, or 100? Does our beautiful pattern just collapse?
Let's find out. Let's blow this thing wide open. Instead of 3 colors, let's just say we have M colors, where M can be any whole number you can think of. You know what? The logic doesn't even flinch. It stays exactly the same. The total number of colorings is now M to the power of P. The number of special solid color necklaces is M, and everything else still falls into perfect P-packs.
And with that one last step, we've done it. We've arrived. What we just proved, just by playing a game with necklaces, is a cornerstone of number theory. It's called Fermat's little theorem, and it says that for any prime p and any integer m, m to the power of p has the same remainder as m when you divide by p. We built it from the ground up just by rotating beads on a string.
So it doesn't matter if we have 4 colors or 5 or 117 colors. That rotational logic is just unshakable. The number of necklaces will always follow this elegant rule. The pictures here might only show a few colors, but the idea they represent is totally universal.
All right, let's do a lightning-fast recap of our journey. Step 1, there are m to the p total ways to color p beads. Step 2, we pull out those m special solid color necklaces that don't change. Step 3, we realize that everything else, because p is prime, falls into perfect groups of size p. And step 4, therefore, the total minus the special cases, m to the p minus m, has to be perfectly divisible by p. And that is Fermat's little theorem.
I mean, how amazing is that? A structure this profound, this fundamental to how numbers work, was just sitting there waiting to be found inside something as simple as counting colored beads. It really makes you wonder, doesn't it? What other deep, beautiful truths are hiding in plain sight, just waiting for us inside the rules of a simple game?